Let's see another example. This is example 2. For this beam, you have to write the equation of the elastic curve using double integration method. EI is constant for this beam. This beam is a cantilever beam. It is subjected to a uniformly distributed load from A to B. Then one couple is there, 50 kilonewton meter, and one point load at the free end of the member, 12 kilonewton. The span of the beam is 9 meter. First of all, we have to calculate the reaction of the beam. You can see it is a fixed supported here, so two reaction will come. One is vertical force and one is moment. So first calculate the moment. If you take moment here and this is, you consider m, then you can write the expression 12 multiplied by 9 minus 50, this is negative as clockwise, 8 multiplied by 5 multiplied by 2.5, it will work at the middle. You are taking moment about point A, and here if you anti-clockwise moment, if you assume, then plus m equals to 0, that will give you m equals to 258 kilonewton meter anti-clockwise. Then make summation of Fy and you will get the vertical reaction here, it is 52 kilonewton. After calculating these reactions, we have to write one moment expression at the end section of the beam. We always consider x from the left side, so this is the end section. We have to write one moment expression. You can see this load is not continuous, but to write the moment expression, we need to maintain the continuity of the loading. So what we'll do, we will extend this loading until the end of the beam. As we are extending this one, we will subtract this one again. So this is the, we extend here, then we subtract the same amount of loading. And we have already calculated this reaction. So now we can take a section towards the end of the beam, and this section is at x distance. So our beam will be look like this one. We have these two reaction, this loading, this couple, this loading, and we are taking section here. So when we'll take this section here, you can write the expression for the moment. We are taking section here means we are putting one line and making it fixed here at distance x. When we'll fix it here, it is like cantilever this side now. One by one we have to draw. For this 52 kilonewton upward loading, the moment diagram will be 52 multiplied by x. For this 258 kilonewton per meter couple, the moment diagram will be this line. It will start from here towards the end of the section, 258 multiplied by x minus 0 power 0. X minus 0 to the power 0 means it is 1. So it will remain 258. But we have to write the moment expression like this way. You can see your table 15.2 in your text. We have to write moment expression like this. So we have done with these two. Next, if we want to write for this uniformly distributed loading, it will start from here and it will go until this point. For this 8 kilonewton per meter, Wx square divided by 2, so W is 8. We will write x minus 0 whole square divided by 2. So this way we can write. For this uniformly distributed loading, we have to write, it is upward, so it will be positive 8 x minus 5. This is the distance x minus 5 whole square divided by 2. And this couple is this one, plus 50 from here to the end of the beam. So we have 5 expression, 1, 2, 3, 4, 5. If we write this 5 expression together, then we can get the moment expression for this beam. So m will be plus this one, plus this one, minus this one, plus this one, minus this one. So your moment expression will be this one. When we'll get the moment expression, then we have to write the moment curvature relationship. That means EI d square y divided by dx square equals to this moment. So you can write EI d square y. Instead of y, you can write delta also. You can write y also, no problem. And this moment expression. If you integrate once, one constant of integration will come. And this is the slope expression. If you integrate twice, you will get the deflection expression. And C1 and C2 is the constant of integration. As we have two constant of integration, we need two boundary condition. As it is a fixed supported beam, we can write the boundary condition at x equals to 0. Support is at the beginning, so at x equals to 0, slope will be 0. dy divided by dx equals to 0. And if you put this thing, dy in the slope equation, you will get C1 equals to 0. Another boundary condition, at x equals to 0, y equals to 0. So from the deflection equation, we can, if we put this value in the deflection expression, we can get C2 also equals to 0. So finally, our equation of the elastic curve will be this one. So this complete your second example.